Okay, so hello and welcome back. So the next thing that we have here is part 4 of question number 1, which is basically a relation R in set Z, the set of integers, defined as R is equal to all the ordered pairs x comma y such that x minus y is an integer. And you want to show that whether R is reflexive, symmetric, and transitive, right? So the condition for R being reflexive was that basically we said that if a comma a belongs to R, for every R belonging to a, then we say that R is reflexive, which means that in this particular case, we are saying that basically R is all the ordered pairs x comma y such that x minus y is an integer. That means that if x minus y is an integer, then x comma y belongs to R. Now we need to see where this works and where this doesn't work. So you know that any two integers, if you subtract any of them from the other one, you will get an integer. That means that basically R can basically contain all the ordered pairs made up of all of the integers basically. And so that means that then for all of the integers basically belonging to the set of integers, then a comma a is going to be a member of R. Another way of saying it is that basically R is the same thing as a times a, or the Cartesian product of a and a. So the Cartesian product of a and a is basically all of the ordered pairs is equal to all of the ordered pairs basically x1 comma y1, x2 comma y2, and so on and so forth all the way up to x of n comma y of n, where x1 all the way up to x1, x2, basically x3 all the way up to x of n, where this set basically constitutes Z, and also you can say that y1 comma y2 comma y3 all the way up to y of n constitutes Z, right? So which means that, and therefore you can say that for every a belonging to the set of integers, for every a belonging to the set of integers, a comma a belongs to R, right? Which means that R is reflexive. Let me see if there is another way of saying the same thing, or possibly a better way. Or basically, to make this a little bit simpler, probably if you didn't understand my explanation here, there is also another way of saying the same thing, meaning that since we are saying that R is equal to all the order pairs x comma y, such that x minus y is an integer, then basically for every x belonging to the set Z, x comma x, x comma x, x comma x does belong to R, right? As x minus x is equal to 0 is an integer, right? So that is another way of saying the same thing. Okay, so now about the question whether R is basically symmetric. R is symmetric. What we can say is that, so whether R is symmetric, the condition for being symmetric was that basically we said that if A1 comma A2, the condition was if A1 comma A2 belongs to R, implies that A2 comma A1 belongs to R for all A1 comma A2, for all A1 and A2 belonging to R. That is the condition. Now over here what we have is that basically we are working with the set of integers, and this is basically the rule that, or the relation that we have. We are working with the set of integers, and the relation that we have is all the order pairs x comma y, such that x minus y is an integer. Okay, so so again, so if basically A1 comma A2 belongs to R, so basically if I take this as an assumption that if A1 comma A2 belongs to R, that implies that basically A1 minus A2 is an integer. Which implies that basically if A1 minus A2 is an integer, that means that both A1 and A2 could be simple integers, meaning that A1 and A2 are integers. Now if A1 comma A2 are integers, that also implies that A2 minus A1 is also an integer. Which implies that A2 comma A1, based on this rule here, A2 comma A1 based on this rule also belongs to R, which means that A1 comma A2 belongs to R, implies that A2 comma A1 belongs to R, for all A1 and A2, for all A1 and A2, for all A1 and A2 belonging to Z, which means that R is symmetric. Right? So that is that. And in case you didn't understand my logic here, which was pretty simple, you can also basically the same idea, you can say it in this way, meaning that you can say that for every x, meaning that you can say that for every x comma y belonging to Z, for every x comma y belonging to Z, if x comma y belongs to R, then x minus y is an integer. X minus y is an integer. Right? Now this is based on the rule that we had here, based on the rule that we had in R. We said that if basically R is equal to all the order pairs x comma y, such that x minus y is an integer, which means that basically if x comma y belongs to the set Z, for every x comma y belonging to the set Z, if x comma y belongs to R, then x minus y is an integer. Then x minus y is an integer. And so what that means that minus of negative x comma y is also an integer. Right? Which implies that basically negative x minus y is y minus x is also an integer. Which implies that y comma x belongs to R, right? Belongs to R, which means that basically R is symmetric. So this is based on the solution set that we had before, or no, I'm sorry, based on the solution set that we had from the Tiwari Academy. I'm usually more convenient with the line, my own line of reasoning. Whenever I cannot come up with a line of reasoning, of course I use their line of reasoning. But otherwise, if there is any sort of line of reasoning that you can think of yourself, it's usually more convenient and easier for you to understand. Of course, as long as that's correct. Logically correct. Now, the third part of this question is that if basically you want to check whether R is transitive. Whether R is transitive. So the condition for R being transitive is that if A1, A2, if A1, A2 belongs to R and A2, A3 also belongs to R, implies that A1, A3, A1, A3, A1, A3 also belongs to R for all A1, A2, and A3 belonging to the set Z, or belonging to the set, let's say, for all belonging to the set A, basically. This is general condition, of course. Okay, so belonging to the set A, right? This is the condition that we have. Now we want to check whether R is transitive, right? So again, we were working with the set of integers, and this was my relation. So basically we are working on the set of integers, and my relation is basically all the order pairs x comma y such that x minus y is an integer. So let's see how we can show that. Let's see how we can find out whether R is transitive or not. Okay, so now since I want to prove that basically, this statement, I want to prove that this statement implies this statement, I can make this my assumption, meaning that I can say that, let's assume that basically A1, or let's write it as x1 comma y1 and y1 comma y2, for example, belong to R for some x1, y1 and y2 belonging to the set of integers, right? So that implies that basically, since these two belong to R, based on the condition that we had for R, which was if x comma y basically belongs to R, then x minus y is an integer, then I can say that basically x1 minus y1 and y1 minus y2 are integers. Which means that now this part alone implies that x1 and y1 belong to the set of integers, and this part means that y1 minus y2, y1 and y2 belong to the set of integers, right? So that means that basically x1 and y2 belong to the set of integers. If x1 and y2 belong to the set of integers, what that means is that again, based on the rule that basically we had here, we said that x comma y belongs to R if x minus y is an integer. So if if x1 and y2 belong to the set of integers, that means that x1 minus x1 minus y2 is an integer, right? So if this is an integer, then it belongs to the set of it does belong to the. So over here what we are saying is that basically R is equal to all the order pairs x comma y, meaning that x comma y belongs to R if x minus y is an integer. So if x minus y is an integer, that means that it belongs to the set of R. That means that basically x1 comma y2 belongs to the set of R, right? So we have assumed that, so this was my assumption, we have assumed that basically x1 comma y1 and y1 comma y2 belongs to R, and that implies that x1 comma y2 belongs to R, which means that basically R is transitive. R is transitive. R is transitive, right? Now, in case you didn't understand my logic here, you can also say that let x comma y and y comma z belong to R, where x, y, and z belong to the set of integers, right? Now, if that is the case, then you can say that x minus y and y minus z are integers, right? They are integers. And so if I can write basically x minus z, I can write it as, now if I write x minus y plus y minus z plus y minus z is equal to x minus y plus y minus z, and these two will cancel out and you have x minus z, right? So I have two integers here, x minus y and y minus z, and I have added them together. So of course I will get an integer. When you add two integers together, you will get an integer. That means that basically x minus z is an integer. Which means that basically x comma z belongs to R, and therefore R is transitive. So that was basically part 4 of this question. Part 5 of this question is as follows. Part 5 of this question is relation R in a set A of human beings in a town at a particular time. So you have part 5 of exercise 1. So the question is relation R in the set A of human beings, in the set A of human beings in a town at a particular time, in a town at a particular time, at a particular time given by R is equal to, and this question has a couple of parts. This question does have a couple of parts. Let's see. It's reflexive, symmetric. Okay, so this question has basically part A, part B, part C, part D, and part E. Okay, so given by A, part A, R is equal to all the order pairs x comma y, such that x and y work at the same place. X and y work at the same place. So if that is the case, now we will have to basically solve this part of the problem, meaning that we need to find out whether R is reflexive, symmetric, and transitive here, and then we will change R using the same set, and then we will again find out whether those relations are reflexive, symmetric, and transitive. That's how this question works. So if you want to find out whether R is reflexive, you want to find out whether R is reflexive. So what you need to do is that we say if A comma A belongs to R for every A belonging to A, then we say that basically R is reflexive. Now in this particular case, okay, so here what you can do is that basically we said that the relation R is defined in the set A of human beings in a town at a particular time, given by basically this R, which is R is all the order sets x comma y, such that x and y work at the same place. Such that x comma y works at the same place. Now, based on this condition, basically you can say that x comma x belongs to the set R for every x belonging to the set A, because everybody works at the same place where he works, where he or she works. So based on this reasoning, you can say that x comma x always belongs to R for every x belonging to A, right? Now, to find out whether R is symmetric, to find out whether R is symmetric, the condition is that if basically A1 comma A2 belongs to R, implies that A2 comma A1 also belongs to R for all A1 comma A2 belonging to A. Belonging to A, which means that basically if I assume that some A1 comma A2 belongs to R, so now let's assume that, for example, let some x1 comma x2, now let's assume that some x1 comma x2, x1 comma y1, for example, belongs to A, for example. So if x1 comma y1 belongs to A, that means that basically x1 and y1 work at the same place. Right? Which implies that basically y1 and x1 also work at the same place, which implies that y1 comma x1 also belongs to R, right? So I made the assumption that this part was true, and I made the assumption that this part was true, and then I proved that this part was also true, which means that basically R is symmetric, right? Now, in order to find out whether R is transitive, what you can basically, the condition that we have is that if A1 comma A2 belongs to R and A2 comma A3 belongs to R, if that implies that A1 comma A3 also belongs to R for all A1, A2 and A3 belonging to A, for example. That's the condition, meaning that basically you can make the assumption that, for example, this is true, and then show that this part is true, and then you have proof that R is transitive. So now let's assume that some x1 comma, so let us assume that some x1 comma y1 belongs to A, and also some y1 comma y2 belongs to A. Since we are saying that basically x1 and y1 work at the same place, that means that basically x1 and y1 work at the same place. That also means that y1 and y2 also work at the same place. Which means that x1 and y2 which implies that x1 and y2 work at the same place, right? And so that implies that means that basically x1 comma y2 does belong to R, right? x1 comma y2 belongs to R, which means that R is transitive. R is transitive. Now, the second part of the fifth part of question number 1. So this is part 2 of part 5 of exercise 1 is basically, we have again the same set, which is basically, okay, so we have again the same set, which is basically the set A of human beings working at the same place in a particular time, and the set R in this case is basically x and y live in the same locality, and the relation on this set is basically all the ordered pairs x comma y, such that x and y live in the same locality. So you want to know whether R is symmetric, reflexive, and transitive. So again, to check whether R is reflexive, basically the condition for that is that if A comma A belongs to R for all A belonging to A, right? So basically here we are dealing with the set of human beings working at the same place in particular time, and basically R is all the ordered pairs x comma y, such that x comma y live in the same locality. So what that means is that, let's suppose that what that means is that basically x comma x belongs to R for all x belonging to A, because x and x live in the same locality, right? Which means that R is basically reflexive. On the other hand, if you want to check whether R is symmetric, the condition is that if basically A1 comma A2 belongs to R, implies that A2 comma A1 also belongs to R for all A1 and A2 belonging to A, right? So now let's assume that basically x1 comma y1 belongs to R, which means that x1 comma y1 live in the same locality, right? That means in turn that y1 comma x1 also live in the same locality. Which in turn implies that basically y1 comma x1 also belongs to R, right? So we have assumed that x1 comma y1 belongs to R, and we have proved that y1 comma x1 belongs to R, which means that R is symmetric. Now, the third part of this question is if you want to check whether R is transitive. Whether R is transitive, and the condition for that is that if A1 comma A2 belonging to R and A2 comma A3 belonging to R, if that implies that A1 comma A3 belongs to R for all basically A1, A2 and A3 belonging to A, right? So belonging to A. Okay, so now in order to check whether R is transitive, we said that basically over here we said that basically A is the set of all human beings working at the same place in a particular time, and R is basically all the order pairs x comma y such that x and y live in the same locality. So if I assume that basically some x1 y1, if I assume that some x1 y1 and some x2 some y1 and y2 belong to the set of R, then what that means is that x1 and y1 live in the same locality, and also basically y1 and y2 live in the same locality, which in turn means that x1 and y2 live in the same locality, right? Which means that basically x1 comma y2 belongs to R. So we have assumed that x1 y1 and y1 y2 belongs to R, and we have proved that x1 y2 belongs to R, which means that basically R is transitive. R is transitive. So that was part 2 the second part of the fifth part of question number, that was the second part of the fifth part of exercise number 1. Now the third part, for which we need so now the third part of the fifth part of exercise 1 is basically we have again the same set A, we have again the same set A of human beings, basically in a town at a particular time. Right? And this is actually part C. And the previous parts were A and B. Right? So this is part C. So, and R in this case is basically all the ordered set x comma y such that x is exactly 7 meters taller than y, such that x is exactly 7 meters taller than y. So now to show that that R is reflexive, the condition is if basically A comma A belongs to R for every A belonging to the set A. Right? Now if I assume that basically if I assume that some x belongs to R, now of course you know that x comma x does not belong to R, because x is not 7 centimeters or 7 meters. I don't really know whether that was 7 centimeters or 7 meters. That is 7 centimeters. That is 7 centimeters, okay? Now, x can never be 7 centimeters taller than himself or herself, right? And for the same reason, x comma x does not belong to R, which means that R is not reflexive. Now to check whether R is symmetric, we said that if this condition is true, meaning that if A1 comma A2 belonging to R implies that A2 comma A1 also belongs to R for all A1 and for all A1 and A2 belonging to A, right? Now let's assume that some A1, A2, or let's assume that some x1 comma x1 comma y1 belongs to R, which means that basically x is exactly 7 centimeters taller than y, which means that x1 is x1 is 7 centimeters taller than y1, right? And of course, if x1 is 7 centimeters taller than y1, that does not mean that y1 is 7 centimeters is also 7 centimeters taller than x1. That means that y1 is 7 centimeters shorter than x1, which means that y1 comma x1 does not belong to R, which means that R is not symmetric, Now the condition for R being transitive is that if basically A1 comma A2 and A2 comma A3 belonging to R implies that A1 comma A3 also belongs to R for all A1, A2 and A3 belonging to A, right? That is the condition. Now let's assume that some x1 comma y1 belongs to R, and also some y1 comma y2 also belongs to R. That means that x1 is 7 centimeters shorter than y1 and y1 is 7 centimeters shorter than y2. That means that implies that basically x1 is 7 centimeters shorter than y1 and y1 is 7 centimeters shorter than y2, right? Which means that x1 is 7 centimeters plus 7 centimeters, which is basically 14 centimeters shorter than y2, which means that basically x1 comma y2 does not belong to R, which means that R is not transitive. Right? So this was part actually that's longer than, I made a mistake here, right? This is supposed to be longer than instead of shorter, you should say longer. That's a part of the problem. Okay. So basically x1 is 7 centimeters longer than y1 and y1 is 7 centimeters longer than y2, which means that basically when x1 is 7 centimeters longer than y1 and y1 is 7 centimeters longer than y2, that means that x1 is 7 plus 7 centimeters longer than basically y2, which well of course means that x1 comma y2 does not belong to R, which means that R is not transitive. Okay, so this was part C. There is also part D here. There is also part D here, but then D and E related to question number 1, which we will do in the next video. I'll see you in the next video.